writing out the r prime in both cases and neglected to write down the delta t, so that our sum is going to be the sum of these expressions, each on the ith interval, and that's going to approach the integral, which is going to approach the integral then of mx prime plus ny prime plus pz prime dt, where t runs over the partition from a to b, not from a to t. So I'm going to have to fix that. Writing then this result in detail, we see that the integral is the integral from a to b of what? M of x of t, y of t, z of t, times write it dx dt, plus n of x of t, y of t, z of t, times dy dt, plus, probably don't have room to squeeze that in, so I'm going to write it a little bit lower, p of x of t, y of t, z of t, times dz dt, quantity with respect to t. As a more specific example, consider this function on the elliptical path as pictured. Parameterize the path, and a simple parameterization for this path would be x equals cosine of, now let's see, we could let it be the cosine of t. X goes from 1 to 0, so that our t would have to go from 0 to pi over 2. And let's see, do we want to do that, or do we want to let just x equal cosine of pi over 2t and let t go from 0 to 1? Either way, we're going to be taking the cosine of 0 at the initial point, the cosine of pi over 2 at the final point. So this is actually going to work out a little better. We're not going to have, well, let's back up. Okay, I started to say we're not going to have to worry about chain rule and so forth with this parameterization, and of course I led myself into a contradiction. I'm going to go back to x equals cosine of t, and I'm going to let t go from 0 to pi over 2. Now note, either of these parameterizations will take our x value from 1 to 0 as we go over the corresponding interval. But I'm going to choose this interval, just make the integral expressions a little easier to deal with and a little less messy. Okay, now we're going to then let y equal 2 times the sine of t, t, of course, having to have the same interval for y as it does for x, and z equal to x, which would then be z just equal to cosine of t, again 0 less than or equal to t less than or equal to pi over 2. We partition our t interval and the ith interval of the partition has sample point that we'll call Ti star. just to have a picture of what we're looking at. Like we have a part of the path and we have an ith interval. There's a delta S on this interval. That'll be delta S sub I and a sample point Ti star somewhere within the interval. And everything is evaluated at this sample point. Now what's our delta S sub I? Delta S sub I is R prime times delta T. Now R prime is, let's back up, R is the vector function. R of T is X of Ti plus Y of Tj plus Z of Tk. So R prime is the derivative of this function, and it's evaluated at the point Ti star. This represents, if T is a time parameter, if we interpret T as a time parameter, then this is a velocity. Whatever the interpretation of our T parameter, or even if we don't have an interpretation, the delta Si is still R prime of Ti star times delta T. For the given parameterization, of course, R prime of T is just X prime I plus Y prime J plus Z prime K. This equals what? X prime is the negative of the sine of T, so that's negative sine of Ti star times I. Derivative of 2 sine T is 2 cosine T, so that's going to be 2 cosine of Ti star times J, plus derivative of Z, being the derivative of cosine, that's going to be negative sine of Ti star times K. F at X of Ti star, Y of Ti star, Z of Ti star. Because remember, we're wanting to do F dot delta S. We're going to evaluate all the X, Y, and Z components, or the X, Y, and Z expressions at Ti star. So that's going to be what? XY is going to be cosine of Ti star times 2 sine of Ti star. So the XY is going to be 2 cosine of Ti star sine of Ti star. That's going to be times the I. The J component is going to be X times Z, which is just going to be the cosine times the cosine. So that's going to be cosine squared of Ti star times J, and then plus YZ times K. YZ is going to be 2 sine of Ti star cosine of Ti star, and that's going to be times the K vector. From this, it's easy to see then that F dot delta Si is what? I component times I component, the sine of Ti star times 2 cosine Ti star sine Ti star, and that's going to be then 2 cosine of Ti star sine squared of Ti star. And then plus what? J component of this times the J component, and I back up a second, we have a negative sine of Ti star here, so this will be negative. Okay, when we go to the J component, we have 2 times the cosine squared. That basically gives us 2 times, not basically, it just plain gives us 2 times cosine cubed of Ti star. And then the K component times the K component will be another negative 2 times sine squared of ti star cosine of ti star. The sum of our f dot delta s i's is then the sum of these expressions. Now I'm going to consolidate this expression and this expression are like terms, so we're going to have negative 4 cosine of ti sine squared of ti star plus 2 cosine cubed of ti star. And that's the sum over all the intervals. I'm being a little sloppy with that notation, but this should be fairly clear. And that's going to approach then the interval of what? Negative 4 cosine squared of t sine squared of t, and it's just cosine of t, not cosine squared, plus then 2 cosine cubed of t quantity dt, where t goes from 0 to pi over 2, because of course we originally partitioned the integral from 0 to pi over 2. This clip is already long enough, so I'm not going to go through the details of evaluating this integral. It's very simple. Take the cosine cubed and express it as cosine squared times the sine of t, or let's say, no, let's stick with that. And then we're going to have two expressions that are easily integrated by substitution. In this expression, we could let u equal sine squared of t, so the du is cosine of t. Over here, we get something almost as simple, and the integral turns out to be very easy. You won't always follow this entire process to set up an integral, but it should always be available to you. You should always think through this process in your head at least. In practice, what you'll probably end up doing when confronted with a problem like this is simply parameterize the path and then immediately write down this expression for f dot ds, or f dot delta s. You'll put your x functions in for your x, y's, and z's here. You use your parameterization here, and you'll very quickly get to the integral. But every once in a while, you should go back and check the entire process. I've quickly integrated here how we integrate the cosine cubed of t, separating that into 1 minus sine squared, times the cosine, letting u equal sine t, du equal cosine t dt, giving us the integral 1 minus u squared du, which just gives us u minus u cubed over 3. U is the sine of t, so right here is an antiderivative of the cosine cubed of t. Of course, you would have to evaluate that between the limits, and you would use a very similar technique here. Just let u equal sine t. You're going to get an integral of negative 4u squared du. Very simple.